Hello, I am Guanzli Yu from Bihang University. I am going to present our work VoteHMR, Occlusion-Aware Voting Network for Robust 3D Human Mesh Recovery from Partial Point Clouds. In this paper, we focus on human mesh recovery from partial point clouds captured by consumer-level depth sensors such as Kinect and TOF camera. Existing partial human point cloud data, either synthetic data or real data, contains complex self-occlusions and missing body parts. Besides, the severe noises in real data add additional difficulty to stable human surface estimation. Thus, there are two key challenges that need to be addressed in human mesh recovery from partial point clouds: coping with complex self-occlusions and missing parts for robust pose estimation, sustaining reasonable shape reconstruction without the interference of severe noises. Recent works have also tried to recover 3D human meshes from point clouds. Jiang et al. Propose a skeleton-aware network to predict human mesh from complete human point cloud scans, but failed to generalize well to partial human scans. Wang et al. Used a course-defined spatial temporal mesh attention convolution module to predict human meshes from sequences of partial point clouds. In their framework, temporal dependencies are vital to rectify the flaws caused by partial scans. However, existing approaches are not yet able to reliably cope with a single frame of partial point clouds that are affected with severe self-occlusions and noises. VoteNet is the first deep learning methods that successfully applied Hough voting for object detection on the point clouds. After passing the input point cloud through a backbone network, VoteNet sample a set of seed points and generate votes from their features. Votes are targeted to reach object centers. As a result, vote clusters emerge near object centers and in turn, can be aggregated through a learned module to generate box proposals. We argue that vote mechanism can be adopted in human mesh recovery from partial point clouds. Voting mechanism can be used to gather enough reliable points to discover the joint-level shape representations around the visible 3D skeleton joints and further used to human mesh recovery. Hough voting mechanism is beneficial to gather sparse points from visible human parts for discovering observed skeleton joints and their shape representations and eliminate the distortions on the generated meshes when interfered with by the flaws of the input point clouds. In this paper, we propose an occlusion-aware voting network for robust human shape reconstruction from a single frame of partial point clouds, named VoteHMR, that tackles the aforementioned challenges using an end-to-end learnable framework. The input of our VoteHMR is a point cloud, with a 3D coordinate for each of the A points. Such an input typically comes from depth sensors that scan partial views of the 3D human surfaces. The outputs are two sets of SMPL parameters. Global parameters controls the body shape and the global orientation, and local parameters indicates the relative rotations of the articulated skeleton joints. VoteHMR consists of four main modules: a partial vote generation and clustering module to cluster votes for joint-level feature association, an occlusion-aware joint completion module to fill in the missing joint features, a local parameter regressor, and a global parameter regressor to separately predict the local and global parameters of SMPL model. We will elaborate on these four modules in the following parts. In partial vote generation and clustering module, we aim at generating a vote for each input point, where each vote has a high-dimensional feature vector, a body part segmentation score vector, and a 3D coordinate offset towards its nearest skeleton joint. These votes within the same segmentation results are then grouped into joint-level vote clusters, representing the skeleton joint of the corresponding segment. There are three major steps. In the first step, a point cloud feature learning backbone network. We leverage PointNet++ with multiple set abstraction layers and feature propagation layers to extract features for each input point. A partial vote generation module simultaneously predicting three components of each vote, where segmentation score vector and 3D coordinate offset are supervised by segmentation loss and vote regression loss respectively. Vote clustering module group and aggregate votes within the same segmentation. Results are then grouped into joint-level vote clusters, representing the skeleton joint of the corresponding segment. Note that the input point clouds may only contain the partial human body scans, thus the output joint features may also partially fill the kinematic tree. In vote clustering module, we set joints with confidence score below a predefined threshold as occluded, and thus set the corresponding joint positions and features to be 0. We use an occlusion-aware joint completion module to fill in the missing joint features as well as the joint positions from the previous stage. We first concatenate the joint position and feature in the channel dimensions, and then list them in the order of the kinematic tree. We use a two-layer MLP network to transform incomplete joint features into the completed joint features, and then an additional FC layer for predicting refined joint positions. In the Global Parameter Regression module, we argue that the combination of global features and skeleton-based features can well describe the global shape information. We conduct a feature aggregation method similar to the edge convolution. We apply a cross-attention module to align global features and local joint features. Then the edge convolution operation is performed between attentive global feature and each joint feature. The resultant features are further fed into a FC layer to predict global parameters. In Local Parameter Regression module, we employ two layers graph convolution networks onto the skeleton graph to incorporate contextual relations, where the graph nodes are the completed joint features, the graph edges are the edges in the kinematic tree. The overall loss function for our VoteHMR can be divided into the vote generation loss, the parameter regression loss for the global and local parameters, and the model fitting loss. Vote generation loss includes the segmentation loss and vote regression loss to supervised vote results. In parameter regression loss, we supervised the global and local parameters of SMPL model. The model fitting loss includes the vertex fitting loss, skeleton fitting loss, and a chamfer loss. VoteHMR is trained on synthetic datasets since they provide ground truth SMPL models for each input point cloud. We first conduct our experiments on two synthetic datasets, Surreal and dFaust. We compare VoteHMR with two depth image-based human mesh recovery methods by retraining the recently RGB-based HMR and GraphCMR methods onto depth data. We also compare our model with 3D human mesh recovery methods upon the point clouds. Our method outperforms all baseline methods on PVE metric. We provide qualitative results on the Surreal datasets. Compared with the baseline methods, our method achieves more reliable detection results with more accurate human mesh and lower vertex error. We also evaluate the generalization ability of our VoteHMR on the real data in comparison to the point cloud-based methods. All methods are tested on the Berkeley MHAD dataset but trained on the Surreal and dFaust dataset. We report both results before and after the weekly supervised fine-tuning scheme is frequently used in the previous methods. The reported results before the weekly supervised fine-tuning can better indicate the capabilities of different feed-forward networks of these methods without the interference of the aforementioned post-processing. Our proposed method achieves significantly better performances than other methods, whether before or after weekly supervised fine-tuning. We visualized the initial results on MHAD dataset. Without the weekly supervised fine-tuning scheme, previous methods usually predict incorrect poses, manifesting that their methods are sensitive to the domains of the training data and much less robust to changes in the point clouds. We conduct a list of ablation studies of our VoteHMR. Our method with partial vote generation and clustering can produce results with much lower errors than the counterpart baseline method does. Qualitative results show that the occluded hand fails to be accurately recovered without the joint completion module. The result without global parameter regression estimates giant shape error compared to the result with our complete method. We also conduct a list of experiment to show our model's robustness against noise and point numbers. We compares different methods about the PVE at different noise levels on the serial test set. Each point in a test sample is added a random 3D noise offset according to a given standard deviation. Our proposed methods VoteHMR present the lowest PVE scores in all the noise levels. We also observed that our method do not significantly distort the pose predictions when facing different levels of noises. The increase of PVE scores is mainly caused by inevitable prediction errors of shape parameters due to large noise variance. We also shows the PVE scores of different point cloud-based methods against the varying sizes of the input point clouds. The input point clouds are randomly sampled to different point numbers. The qualitative results demonstrate the robustness of our model compared with counterpart point cloud-based methods. The visualization results show that our model performs well, even when the input point clouds only have 250 points. In summary, the contributions of this paper are threefold. First, we proposed the first method that successfully apply Hough voting to achieve parametric human shape reconstruction from a single frame of partial point clouds. Second, VoteHMR achieves certain robustness over complex occlusions, noises, and sparsity that frequently occur in the point clouds. We achieved the state-of-the-art human mesh recovery performances on two benchmark datasets, Serial and DFaust, with additional nice generalization towards real-world datasets such as Berkeley MHAD.